Okay, everybody, this lesson is going to be about significant figure operations. Now that we've learned how to count significant figures, we're going to be able to do math operations using significant figures: addition, subtraction, multiplication, and division. So remember, the goal behind all these significant figures is that we're trying to make sure that our measurements that we're reporting in a lab are not any more precise than our least precise measurement. So if we look at the beaker that I've got right here, this is only measured to the tens place here, and then this 3 is estimated. So we only really have, we don't have very much precision in this. We could really be off by quite a bit here. If we look at our graduated cylinder, we measured this one to the tenths place, this 5 right here. This is supposed to be a 2. But we estimated this 2 right here at the end. And so we have a little bit more precision than with our beaker. And our volumetric flask, even though there's only one little line on here, these are very, very precise. And they will measure all the way to the hundredths place, this one right here. This 0.01, we're measuring all the way there. So we have a lot of precision in that measurement. But if we added all of these numbers up, we got something like 1155.21 milliliters. And so this measurement, when we added all these together, it looks really precise for so much liquid. And so when we would report this to somebody, they would be like, well, how did you get that precise with all of them? And they would assume that we measured all of the liquids with something as precise as this one, when in all reality, we didn't do that at all. We measured most of this liquid, or I mean not most of it, a good part of this liquid, with a beaker, right, 153 milliliters, which really could have been 154 milliliters if we would have looked at it a little differently. The guy next to us might have said 155 milliliters. And so we can't report this number as being that precise because we don't know that number to that precision. And so that's why we use significant figures, and that's why our rules that we're going to use today for operations are really important, so that we can make sure that we are reporting the right amount of precision when to other people. So before we get started, we've got to cover some rounding rules just to make sure we're all on the same page. If we have 1.52 and we are trying to round to the tenths place, we look to the number behind it and we see a 2, which is less than 5. So that means this is closer to 1.5 than it is to 1.6, and we're going to round there. If we have a number like 1.58 when we're rounding the tenths place, we look to the number behind it, and we see that that is an 8, it is over 5, so this number is closer to 1.6 than it is to 1.5, and so we're going to go there. If we have a number like 1.55, oops, that's a 5. If we have a number like this and we're trying to round to the tenths place, now we look back and we have a 5, so we are literally halfway between 1.6 and 1.5, like exactly halfway, and we don't know any of the other numbers out here. We're going to round this number to 1.6. We're just going to round it up. We're going to round half up. There's some other rules that you can get into with how to round something like this. We are not going to cover that in this video. We're going to round it up to 1.6. So with addition and subtraction, as we get into these rules, you're going to first count the number of decimal places in the decimal portion of each number in the problem. So let's say we had a number or a problem like 2.5 plus 0.123. And we are going to add that, and we want to know what our precision is here. So first we count the number of decimal places in the decimal portion. This one's got 1, so we've got 1 decimal place. This one's got 3 decimal places. Then we add and subtract normally, and so we are going to get 2.623 for our number. Add and subtract normally, and I'm going to take that 2.623, and we're going to round that number to the least number of places in the decimal portion of any number in the problem. Now what does that mean? That means that if this number here has 1 decimal place and this number here has 3 decimal places, that we are going to round this number here to 1 decimal place, which would be this number right here. So we look to the back, we see a 2, and we round this to 2.6. And that is our final answer. We have no more precision than we started with because our least precise number in our starting problem had 1 decimal place, and that's what we ended up with in our final answer. So let's say we had a problem like this. We have 1 plus 523.46. So we're going to count the number of significant figures, or the number of decimal places in each decimal portion of the problem. This one has 0 decimal places, and this one has 2 decimal places. And so when we add these two together, we get a number like 524.46. we are going to round to the least number of decimal places, which is this 0 right here. And so we are going to round to this number here, this 4. We look back, check out the one behind it, and we see 524 is our final answer because we don't want to have any decimal places in this number because our original did not have any decimal places. So let's say I had this problem. I had 2.473 plus 52.5762934578, and I got this number right here. Now I got to be able to figure out how many decimal places should I have in my final answer. So I first follow my rules because it doesn't matter how big the number is, the rules still work. So I count the number of decimal places in the decimal portion in each part, in each number that we're starting with. So we have 3, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. So I have 3 decimal places in my first one, and I have 10 in my second one. And so I'm going to add or subtract normally, which I already did. And then I'm going to round the answer to the least number of places in the decimal portion of any number in the problem, which is this number 3 right here. And so I'm going to look for 3 decimal places. I'm rounding to right here. And so my final answer is 55.049. And that would be my final answer because that has the same number of precision as either one of, or of the least precise number that I started with. So that's addition and subtraction, and now we're going to go on to multiplication and division. So how does this work? There's only a small little change, but it is a significant change. significant change. We're doing significant figures. Anyways, so there's a small little change. You got to notice that this has changed from our last ones. Before in addition and subtraction, we were counting the number of decimal places, and now we're counting the number of significant figures in both parts of this, both in our starting numbers and in our ending number. And that is going to be a very important distinction to make. So if we had, let's say we had 2.5 times 3.42. Well, we're going to count the number of significant figures in each measurement in the problem. And so this one, oops, I don't want to do that in black. We want to do that in yellow. Let's say this one here has 2 significant figures now. And this 3.42 has 3 because all of those are non-zero numbers. We are going to multiply and divide normally, and my calculator gives me the number of 8.55. Well, this looks pretty good because it's got the same number of digits as 3.42, so that should be okay. Well, we actually have to round this one to the least number of significant figures. Now this 2 is going to be our least number of significant figures. So we have to round this to 2 sig figs. And so I'm going to be rounding it so that it ends up with 2 sig figs. And so I'm going to be rounding it to 8.5, whatever that number ends up being. And so if I'm going to write that down here, I'm looking at my 8.5, I'm looking back to this number, and I'm going to end up with 8.6 because this number ends up with 2 sig figs. And so that's going to have the same amount of precision as our least precise starting number. So let's say we had this problem right here, 3.10 times 4.520. So we're going to first count the number of significant figures in each measurement in the problem. This one is 3 significant figures. Remember, we have 2 non-zero numbers, and then we have a 0 to the right of a number after a decimal place, so that is a significant number. We also have 4 significant figures in this one. We have 4.52. Those are all significant. And we have a 0 after the decimal place in that one. We're going to multiply and divide normally. So what we end up getting from this is, from what my calculator says, is 0.6858 is what I get. And then we are going to finally round the answer to the least number of significant figures of the starting measurement, which is 3, this one right here. And so we have to round this so that it ends up with 3 significant figures, which would be that 5 right there. So our final answer is 0.686. 3 significant figures, and we have no more precision than what we started with in a multiplication problem. Let's say we had this problem, 2.33 times 6.085 times 2.1. We are going to start off by fixing our multiplication symbol right here, hopefully. And then we're going to go and we're going to count the number of significant figures in each measurement in the problem. We have 3 right here. We have 4 here because this 0 is between significant digits, so it counts. And then we have 2 here. And so then we're going to multiply normally. So we end up with 2 29.773905 from what my calculator says. And then we're going to round to the least number of significant figures of the starting measurements, which would be this 2 right here. So we have to round this number so that it has 2 significant figures. And you can see that this is where significant figure rules in multiplication can be really important, because this number that we ended up with looks like it is extremely precise with all those decimal places. And so if we just left it there, we could get entered into like some sort of science hall of fame for the most precise measurement ever. Probably not, but people wouldn't believe that you actually measured something that precise, and we'd be lying about it. And so we've got to be very accurate with the way that we're measuring these. And so we've got to round this last number so that it has 2 significant digits, which would be that 9 right there. And so as I measure this, or as I round this, I'm going to round it to 30, right? Because I take that 9, look back at the 7, well, it's above 5, so I'm going to round up to 0, and I'm going to add that 1 right up there to the 2. Now, the problem is if I leave this 30 right here, I only have 1 significant digit. If someone was to read this 30, they would only say that's got 1 significant figure based off our rules. We've got 1 for non-zero numbers, and that 0 at the end is a 0 coming after a whole number, so it doesn't count. So what we have to do here to make sure that we are leaving the right number of significant figures is we put that decimal there. Well, now we have 2 sig figs. And so 30 with a decimal place after, it looks a little bit funny, but that decimal place is very important, so we can make sure that we have 2 sig figs. Let's say that there was an experiment going on that was trying to determine the probability that a certain person would win a sweepstakes or something. You know, like you enter your name in for a new car in the mall, and you put a piece of paper in a little bucket, and they draw a name out, and they call you if you want it. And so let's say that someone had a probability of winning when they put their name in of 0.0505%. And so let's say that we had 4 people that all got together. Let's say we had 4 people who all got together, and they were all going to put their name in on this deal. And so let's say we had them. These 4 guys are all going together, and they're all going to enter their name in this thing. And they want to know what's the probability that one of us is going to win this thing. And so we can figure out the probability really quickly by multiplying 4 by whatever the percentage, because we're taking the percent, the probability that one of them will win it. So this is an or problem. Him, first guy, or this guy, or this guy, or this guy. So we add all the probabilities together to figure this one out. So what we would do if we were doing the math on this one, we would take 4 and we would multiply by the probability of one person, 0.0505%, and then we would get our number. Or our probability that one of them is going to win this thing. And so what we get here is we would get 0.202. And we'd look at this and we'd be like, well, if we're really being sure with significant figures, it's a multiplication problem. So this one only has 1 significant figure, and this one has 3. And so we got to round this number to 1 significant figure, because we got to follow our significant figure rules. And so their real probability would get rounded to 0. We wouldn't have any probability at the end. This one does not follow significant figure probability rules, or significant figure rules. Well, it kind of does, because there's a little exception to our significant figure rules. If we have exact numbers, exact counted numbers, like all of these are 1 person, 2 person, 3 person, and 4 person. There's no uncertainty in any of these numbers. We counted these numbers. This does not count for significant figures rules. We do not have to round to that number, because we know how many people there are to an infinite precision, is what we call it. Because we have no doubts that there is 4 people here. There is in no case 4.01 people here. There is exactly 4. And so we would report this number as 0.202, because our 4 here does not count for any significant figures numbers, because it is an exact number and it is counted, and so it does not count. And so this is how we would report that percentage. And so I hope that you're feeling a little bit more comfortable with the math operations of significant figures, recognizing that the key difference between them is that in addition and subtraction, we are counting the least number of decimal places and rounding to the least number of those. And in multiplication and division, we are counting the number of significant figures and rounding to the least number of significant figures in the starting measurements.